Okay, so we're back. Let's just recap. So everything has electrons, so everything does induced dipole-dipole bonding. More electrons you have, the stronger the induced dipole, the higher the boiling point. Okay, so that explains the relationship, between the noble gases. Helium has the lowest boiling point, krypton has the highest, and it scales based on number of electrons. But we don't say electrons because, hey, number of electrons, same as number of protons. We'd like to see in the book that relationship between molecular weight and boiling point. Okay, but that's really number of electrons and boiling point. So that's true for everything. Everything has electrons, fair enough, right? So that's always there as an entry-level kind of bonding. Then as we just saw, some lucky molecules have permanent dipoles. They have polar covalent bonds, bonds made of atoms with different electronegativities that makes a separation of charge across that bond, a little bit plus, a little bit minus on the two ends. Permanent dipole does the same thing as the induced, but all the time, okay, so it adds on top. And then we saw in our last slide there that, hey, so things with the same weight, same amount of number of electrons then, same number of electrons pretty much, but the permanent dipole changes with the nature of the atoms involved. The stronger the dipole, the bigger the charge, if you like, the stronger the bond, the higher the boiling point. So that's where we left it. Now, one thing we've talked about from time to time, and this is kind of a wrap up for that, we've talked about salt dissolving in water really, really well. Okay, now salt dissolving in water, if I do an Na ion, right, Na plus ion, right, salt dissolving in water is an example of an ion dipole interaction. All right, because water itself, and I showed you this picture before, water has that structure, right? That's a polar covalent bond, as is that, so that's a little bit, that way, isn't it? My mistake. That's a little bit plus, that's a little bit minus, and we like to draw waters like these little triangles, right? So the minus end will stick to a plus ion. And similarly, if I have Cl over here, the plus end will stick to a minus. So we can have a full charge and a partial charge sticking together, right? So that's an ion dipole intermolecular force, right? And that's really explains why things like ionic solids like salt, table salt, dissolve really well in water, because they stick to the water better than they do each other. And I'll show you my, one of my favorite slides. It's what I call the tractors and trailers slide, right? You've seen this before. So here's a kind of a generic, it may as well be NaCl, right? Na plus, Cl minus. Here are my water molecules, that's O, H, H. So there's the minus end attracting with the plus ion, right? And then you can go front in, that's why I like to talk about tractors. Tractors can hook up in the front or the back. And there's one hooking up in the back, right? So the plus end can hook up a minus ion, drag it off into solution. The minus front can hook up a plus, take it off into solution. Mentioned this before, but why do ions dissolve in solution? Because there's loads of water stuck to them. These bonds are weaker. It's a partial plus and a full minus, not a full, right? But there's more of them. There's like 6 little bonds which overwhelm 4 strong bonds, if you like. So this is Cl minus, that's Na plus. And that's why we have separate mobile ions, if you remember our chat about electrolytes. So if you remember, NaCl solid, which is this thing here, turns into, when we do the, if you like, the complete ionic equation, that one, right? So separate mobile ions, electrolytes, fantastic. All right, so that's why salt dissolves in water. It's because of a special kind of intermolecular force, ion dipole. But again, what have these things all had in common so far? It's always a little bit of plus attracts a little bit of minus, or in this case, a full plus, a little bit of minus. Okay, so they're electrostatic in nature. All right, charges. Now the last one is the strongest. We say the strongest kind of bond till last, and in biology they call it a hydrogen bond. We do call it a hydrogen bond in chemistry sometimes, but we really like to call it a really strong permanent dipole bond. Okay, so it's a special kind of very strong dipole-dipole interaction. Okay, it's the strongest kind of intermolecular force. It's the strongest. That's why nature makes us from certain atoms, right? Nitrogen, oxygen, hydrogen, and carbon, because these are the things that can hydrogen bond the best. Okay, so our internal structure in terms of our cells, our DNA, and things like that, is held together by hydrogen bonds. Okay, so nature has selected the strongest kind of intermolecular force to build us from, which is kind of neat. All right, now when we think about hydrogen bonds, we're looking for what's called the hydrogen bond coordinate, right? So obviously there's going to be hydrogen in there, but X and Y need to be super electronegative, right? So super electronegative things, well, who's the highest? Fluorine. Well, that's great, and in academic examples we can use fluorine, but it only makes one bond, right? So, you know, remember our Lewis, so it's not so great in natural systems. So we don't actually use in our bodies fluorine too much. We use the next two, nitrogen and oxygen, right? So X and Y can be either oxygen, nitrogen, or in some academic examples, fluorine, okay? So on the next page, actually the story of the picture, so we have upper R for the rest of the molecule, right? So here's a molecule which has either a fluorine, oxygen, or a nitrogen, and they have lone pairs, right? Okay. Now if you think about it as part of a molecule, right? So this is electronegative, so the electrons are going to go that way, and that's going to be a little bit minus. All right. Across the way here, hydrogen bond, because the other molecule must have a hydrogen on it, which is attached to, and there's the rest of the molecule. Another super electronegative thing, fluorine, oxygen, or nitrogen, right? Electrons will go that way, a little bit minus, a little bit plus. What have we got? We've got a plus and a minus looking across from each other. It makes a strong dipole-dipole bond, right? So we're looking for, on an atom with a nitrogen, oxygen, or fluorine on it, in a solution with a molecule with a hydrogen stuck to a fluorine, oxygen, or nitrogen, and the rest of the molecule. So if we see this coordinate, if we see this magic coordinate called the hydrogen bond coordinate, they will do this, okay? And you get a really strong bond. All right, so you've got a couple of examples. You can mix and match, right? So you can have, if I look at natural systems, I'm only going to use nitrogen and oxygen, 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 nitrogen, nitrogen, right? So there's one molecule, there's the neighbor, one molecule, there's the neighbor. So that would be an OHN coordinate, OHO coordinate, NHN coordinate, all right? So that's our possibilities. There's also one more, which would be what? So OHN, it would be NHO, right? So I could have an NHO. All right, so let's look at some examples. If we look at water, here's water right here. Now water is a really fantastic molecule, yeah? Because it has the hydrogen bond coordinate, right? So if I look at let's just draw it up here. If I look at a water molecule, it has two lone pairs and two OHs. Fantastic, right? So it's got an OH bond and it's got a lone pair on an electronegative atom. So it's got two of everything almost, right? So this is why water is really cool, because water has a molecular weight of 18 grams per mole. It boils at 373 Kelvin, it's its boiling point. So it must have super strong bonds between the particles, because neon, which boils at 27 Kelvin, weighs more. So neon has more electrons, yet it has a order of magnitude lower boiling point. Why? Because this has super strong intermolecular forces, hydrogen bonds. So it turns out that water can hydrogen bond twice. That's why it's so special. If the molecule makes two super strong bonds, it's going to have a super high boiling point, because you've got to snap two twigs to make it kind of boil, right? Or, break its bonds. So water's crazy, has a super high boiling point. It should boil at 27 Kelvin, but it boils at 373 because it has two super strong hydrogen bonds in the OHO coordinate. Okay. Now ammonia is a gas at room temperature. Obviously water is a liquid, so liquid water has stronger bonds than gaseous ammonia at room temperature. Cool ammonia down, it does form a liquid a little bit below room temperature, but it means its bond is weaker, right? Well, it only makes one of them, right? So it only has the one lone pair, right? So it can't hydrogen bond twice, really. So there's ammonia, it's the NHN coordinate. So we've seen the NHN and OHO, water, ammonia. Okay, of course I can mix and match. I can have water dissolving ammonia. In the lab we've seen NH3 aqueous as a reagent in some of our experiments. That means the ammonia is sticking to the water. It's an OHN system, right? OHN. So that's that top one up there. Okay, so again, as long as you see the coordinate, it works fantastic. All right, now, last one. One very interesting example is DNA, right? So we have these base pairs in DNA, which helps us replicate kind of DNA strands. Okay. Now it turns out this is a base pair, guanine, cytosine, right? And adenine, guanine, right? So it's like a code, yeah? So here's one strand in DNA, here's the other. And when DNA replicates, it very, very, very rarely makes an error, right? And that's very important, okay? Why is it that DNA never makes an error? Because it's got this super strong bonding between the particles here. So I've got 3 hydrogen bonds across the gap there. Okay, this is one strand, this is the other strand. And they're in exactly the same position as the other molecule. So they're matching like jigsaw pieces or like fingers in a glove. Okay, so imagine the analogy, right? So imagine getting your most comfortable pair of gloves and then putting a dab of super glue on the tip of each finger and then putting your fingers in the gloves. Do you ever take the gloves off? No, okay, because that's such a unique match in terms of shape and in terms of strength of bond, it never comes apart, right? Okay, so there's never any mistakes, all right? So that's perfectly bonded. That's why DNA is so great at replicating itself, because of the nature of this hydrogen bond between DNA strands. Okay, so there's an example in the real world. Now, what about your test? Well, bottom line is hydrogen bonding, because it is so strong compared to the others, it completely blows the others out of the water, okay? Now, if I look here, for example, if I look at the members of column 6 here, yeah, oxygen, sulfur, selenium, etc., right? If I just went down the list here, as they got heavier, you'd expect their boiling points to increase just based on number of electrons, and that's exactly what you see. So if I kind of do a little bit of a trick here, okay? So sulfur, and I just stick H's on them, right? So sulfur, selenium, tellurium. As they get heavier, their boiling points go up, and that's true for any column in the periodic table, right? Okay, as they get heavier, as they go down the column, their boiling points go up, more electrons, all right? If I look at carbon, well, carbon, you know, it's the lightest, so it's, you know, follows the trend. But if I look at the other 3 groups, nitrogen's at the top of this group, oxygen and fluorine, these are the things that can hydrogen bond. So guess what? Their boiling points are completely blown out, right? So they're completely higher. There's water up there, so that's 373 when it should be down here at 27, right? Okay, so that's why. So if you ever see oxygen-hydrogen bonds, fluorine hydrogen bonds, or nitrogen hydrogen bonds, any of those molecules will have super high boiling points compared to anything else, even ones in the same column of similar structure. Okay, so in terms of our summary then, everything does induce dipole-dipole bonding. The more electrons you have, the stronger the bond is. But remember, they say in the book, molecular weight is proportional to boiling point. So you just look at the, you know, you can work out molecular weights from formulas. You'd use that trend to rank them, okay? But it's, again, popping the hood, it's really a number of electrons, which is proportional to weight. Some lucky molecules have permanent dipole-dipoles. Again, the strength of the bond is proportional to the strength of the dipole. And we saw that chart with how things with the same weight, whichever had the highest strength dipole had the highest boiling point, because it had the highest strength bonds between molecules. And finally, if you ever see hydrogen bonding, so if you ever see that, or you ever see sometimes that, those numbers will be massive compared to anything else as we just saw. Okay, all right, so that's the end of the packet. Don't forget, you've got 2 other things to do this semester. You've got your exam, which I'll get to you in detail on later. And, you know, this is the 1st of May I'm writing in this, so hopefully you get to this by the end of the first week of May. And at that time, you'll have, you know, plenty of time to finish that last lab and get it to me, okay? The last lab will probably get posted, oh, today's Friday, so 3rd, 4th of May, something like that. Okay, any questions down below in the discussion? All right.